In this part, we will implement what we've discussed in theory using a short Python script. I'm working in a Jupyter environment and we will be using IBM's Qiskit platform. What is Qiskit? Qiskit is a Python-based library that allows us to build and simulate quantum circuits. It also let us run those circuits on actual quantum computers provided by IBM. Now, for small circuits with only a few qubits, we can simulate them locally or using IBM's simulators. But as the number of qubits increases, simulation becomes extremely resource intensive, and at that point, we would need to run the circuits on a real quantum computer. In our case, we'll be using a simulator just for demonstration purposes. I walk through the code step by step, and I assume that you're somewhat familiar with Python. If you're not, don't worry. I'll try to explain what each line of code does. But if you've never programmed before, it might be a little hard to follow at times. That said, I try to keep it as clear as possible. I won't go into how to install Qiskit or how to set up a Jupyter environment. There are already plenty of good tutorials out there for that. In this video, we'll focus entirely on writing the code that runs the Deutsch-Jozsa algorithm, and at the end, we will see the result and how it confirms the theory we discussed earlier. All right, let's start by going through the code. And first, we need to import a few things. Basically, we need to tell our program which external tools or libraries it should use in order to work. These imports provide functions that aren't built into Python by default, but that we need for quantum programming. First, we import NumPy. So import NumPy as NP. This is a math library for Python, and we will mainly use it to generate random numbers. Later on, we will use it to randomly decide whether our Oracle function should be constant or balanced. Next, we have from Qiskit import quantum circuit transpile. This line, so quantum circuit, gives us all the tools we need to build our quantum circuits, gate by gate. And transpile is used later to optimize our circuit for the backend we want to run it on, whether it's a real quantum computer or just a simulator. Then we have from Qiskit IBM runtime import sampler v2 as sampler. The sampler v2 will later run our circuit and return the measurement results in the form of a probability distribution. After that, we have from Qiskit transpiler import generate preset path manager. This gives us a set of pre-built optimization routines depending on the backend we use. In our case, we will be using a simulator, so this step prepares our circuit for that specific target. Then we have from Qiskit IBM runtime fake provider import fake Almaden v2. This is the simulator we will use. It mimics the real IBM quantum device called Almaden. It behaves like the real hardware but runs locally. And finally, for visualization, we have from Qiskit visualization import plot histogram and import matplotlib point pyplot as plt. These two lines are used at the very end to plot our results, so we can actually see how many times our bit string was measured, shown as a histogram. That's it for the imports. Now let's go on and actually build the circuit. All right, next we define the variable n, which I've already inserted into the code. So n equals 3 here. This simply sets the number of input qubits we want to use in our Deutsch-Jozsa circuit. So in this case, we'll be working with 3 input qubits. Now, the next part of the code is a larger function, and to be honest, I'm not going to explain it in detail because I haven't looked into every single line myself. This function is responsible for generating the oracle for our Deutsch-Jozsa algorithm. That is the black box, which either represents a constant function or a balanced one. But here's the thing, what actually happens inside the oracle doesn't really matter for our purposes. So what matters is simply how it behaves. It either returns 0 for all inputs, so then it is constant, or it returns 0 for half and 1 for the other half, so then it is balanced. This function randomly decides which one to use, constant or balanced, and builds the corresponding quantum circuit to represent that behavior. I didn't write the function myself. It's from IBM's official Qiskit tutorials, and I'm using it here exactly as it is. If you want to dive deeper and understand every step inside the Oracle function, feel free to check out the Qiskit documentation, but in this video, we'll just treat it as a black box that gives us what we need. Now let's move on to the actual construction of our Deutsch-Jozsa circuit. All right, so I've now added the Oracle function to the code, and I explain later what this function actually gives us when we use it in the circuit. For now, just keep in mind that we will call this function later, and it will randomly return either a constant or a balanced function in the form of a quantum gate. Now let's move on and create our first quantum circuit. We do this with the following line of code. So circuit equals quantum circuit n plus 1 n. What does that mean? With quantum circuit, which we imported earlier from Qiskit, we are now creating a quantum circuit object. We pass two values to it. N plus 1 is the number of qubits in our circuit, and n is the number of classical bits. Since we previously defined n equals 3, this means we're creating a circuit with 4 qubits in total, and we will have 3 classical bits for storing the measurement results. Why 4 qubits? Because we need 3 input qubits and 1 output qubit, and we only measure the input qubits, which is why we use n classical bits, not n plus 1. In the next step, we set our output qubit to the state 1. We do that with the following line: circuit point x of n. Remember, earlier we defined n equals 3, so what this line does is apply an x gate, also known as a quantum NOT gate, to qubit number 3. And just as a quick reminder, in programming we always start counting from 0. So our 4 qubits are numbered like this: 0, 1, 2, and 3. That means qubit 0 to 2 are our input qubits, and qubit 3 is our output qubit. By applying an x gate to qubit 3, which equals n, we flip it from the default state 0 to 1. Next, we apply a Hadamard gate to all qubits. Circuit point h, range n plus 1. So range n plus 1 goes from 0 up to, but not including n plus 1. Since n equals 3, this means qubit 0, 1, 2, and 3 all get a Hadamard gate. This puts every qubit into a superposition on a key step of the algorithm. Next, we call the oracle function. So first, we write circuit point barrier. This doesn't change how the circuit works. It's just for visual separation later, so we can clearly see where each part of the circuit begins and ends. Then we call the oracle with oracle equals dj underline function of n. This runs the function we got from IBM and builds a constant or balanced oracle, depending on randomness. Next, we have black box equals oracle point 2 underline gate. This turns the oracle circuit into a custom gate, so we can easily insert it into our main circuit. And then circuit point compose, black box, and in place equals true. This adds the oracle gate into our main circuit, and we use in place equals true, so it updates the circuit directly without returning a new one. And finally, we add another barrier with circuit point barrier, again, just for visual clarity. Now we apply another Hadamard gate, but now just to the input qubits. So we just take n and not n plus 1. Now we measure the circuit using circuit point measure, range n, range n. This means we are measuring all input qubits, qubits 0, 1, and 2, and storing the results in the corresponding classical bits. That's why we use range n for both the qubits and the classical bits. Now it's time to simulate and run the circuit. First, we define our simulator with backend equals fake Almaden v2. This is the fake IBM backend we will use to simulate the circuit. And next, we have PM equals generate preset path manager, backend equals backend, optimization level equals 1. This creates a path manager that optimizes the circuit for the backend, in this case, our simulator. And then we apply it with either underline circuit equals PM run circuit. This runs the optimization and stores the resulting backend ready circuit in either circuit. Next, we define the sampler. Sampler equals sampler backend. This links the sampler to our chosen backend, in our case, the fake Almaden simulator. Then we run the circuit with job equals sampler point run, either circuit, shots equals 1. Here we tell the sampler to execute our optimized circuit once, so shots equals 1, and return the measurement probabilities. Finally, we store the result with result equals job point result. This saves the output of the execution in the variable result. Next, we extract the result from the sampler. Counts equals result 0, point data, point C, point get, underline counts. This gives us the measured bit string and how often each occurred. Since we only use shots equals 1, we expect something like 111 one time, so just one result. Then we print the counts with print counts, and then we extract the bit string itself with bit string equals next iter counts. This gets us the first and only bit string from the dictionary. So now we have to visualize what we have calculated, and for that we print measured bit string, and then we make a if statement. If the bit string equals only zeros, then we print function was constant, and else, so if there were also ones, then we print function was balanced. And then we also print circuit, and then we display the circuit we have created. And then we also print the oracle circuit, which just prints the circuit which is created in this function from IBM. Okay, so now we can execute our little script, and we see that the measured bit string was 000 one time, of course, because we only made one shot, and this is in the wrong direction. I think this belongs here. Yes. So in this case now, because it is every shot is randomized, so we measured in this case 100, And what that means is that the function was balanced, and that is correct. And here we see the circuit. We have our three input qubits and our output qubit. We have the Hadamard gates and the X gate, which flips the output qubit in to one. And then we have the Hadamard gate. Then we have our oracle, which is just one block. So this block here represents this function. And then we have the second Hadamard gates, and then we see here the measurements of the input qubits. And here below we see the oracle circuit. So here you see it. So now we can do another shot, and now we get 0, 0, 0 one time. So the function was constant. And this particular case is the oracle circuit when f of x is always 1. And if f of x is always 0, then we get a circuit which is not exactly the same, but I have to try a few times. So we get always a balanced one, balanced. So here, now we measured 0, 0, 0, but this is not the same circuit as before. This is the circuit when f of x is always 0. Okay, so that was the coding part of the series, and this was also the last video. I hope you could have learned something, and I put every important link in the video description. And yeah, so see you.